A classical bit operates within strict thermodynamic thresholds, resting securely in a binary state. But a quantum bit, or qubit, occupies a continuous state space. When placed in superposition, its state vector is highly delicate, susceptible to constant interference from its surrounding environment. This environmental interaction continuously forces the qubit to lose its quantum properties and collapse into classical reality. We measure this decay through T1 relaxation times, where the qubit loses energy via amplitude damping, and T2 coherence times, where it loses its phase relationship. This environmental decoherence, combined with imperfections in control pulses, results in state-of-the-art physical gate error rates of about 1 in 10,000. But executing industrially relevant algorithms demands logical error rates of 1 in a trillion. Closing an 8-order-of-magnitude gap strictly through isolation techniques and physical material science is widely considered an impossible feat by the physics community. To bypass this physical barrier, researchers rely on quantum error correction. It serves as the algorithmic scaffolding that actively identifies and mitigates errors before they can compound. The objective is fault-tolerant quantum computing. By grouping an expansive array of noisy physical qubits together, the system synthesizes a single, highly reliable logical qubit. Scaling quantum processors relies directly on strict systems engineering and continuous algorithmic error management, rather than attempting to perfectly isolate individual atoms. Correcting a quantum error faces a fundamental constraint. According to the postulates of quantum mechanics, directly observing a superposition state forces it to collapse, destroying the exact computational data we are trying to protect. To monitor errors without triggering this collapse, engineers utilize a mathematical framework called the stabilizer formalism. It allows the system to continually interrogate the hardware without ever reading the active computational data. In practice, the physical data qubit holding the computational state is placed in a lattice and entangled with specialized auxiliary nodes known as ancilla qubits. The system runs a carefully designed stabilizer circuit using local entangling gates. If a bit flip or phase flip alters the data qubit, this local operation maps the parity of that error directly onto the surrounding ancilla. The system then measures the ancilla. This process, called syndrome extraction, yields a classical bit of information, a +1 or a -1. This binary output reveals the exact location and type of the error without exposing the quantum value of the data qubit. Because Pauli operators are self-inverse, the control system reads the syndrome and simply applies the corresponding X, Y, or Z gate back to the physical data qubit, returning it to its intended state. Syndrome extraction operates continuously in the background. It functions as an active immune system, detecting and purging physical errors to keep the overarching algorithm alive. In quantum algorithms, basic Clifford gates can often be analyzed in software after a program finishes, but achieving universal computation requires advanced non-Clifford gates. These instructions dictate a strictly closed-loop process, where physical corrections must occur in real time while the algorithm is actively running. This diagram illustrates the hybrid architecture required to execute that closed loop. Syndrome data must be measured on the quantum processing unit, transmitted to a classical control stack, parsed by a decoding algorithm, and returned as a physical correction pulse. The speed of this cycle is dictated by a strict latency budget. For solid-state platforms like superconducting circuits, native gate times are so fast that classical decoders have mere nanoseconds to interpret the syndrome and send instructions back to the processor. If the classical hardware fails to process the syndrome data faster than the quantum processor generates it, the system enters a catastrophic backlog spiral. During this processing delay, uncorrected physical errors propagate through subsequent operations. They multiply across the lattice, eventually exceeding the code's inherent correction capability and causing an irrecoverable logical failure. Preventing this backlog requires significant classical hardware acceleration. Engineering teams are embedding bespoke decoding algorithms directly onto field-programmable gate arrays and highly specialized ASICs to minimize latency constraints. Artificial intelligence is also moving into the control plane. Specialized 3D convolutional neural networks evaluate complex error syndromes significantly faster and more accurately than traditional open-source software. The ultimate operational speed limit of a quantum computer is bound by the processing throughput of its classical infrastructure. To protect information at scale, engineers construct a logical qubit. The integrity of this macroscopic entity is defined by its code distance, the minimum number of simultaneous physical errors required to successfully enact an undetected logical failure. For over a decade, the industry benchmark has been the surface code. It utilizes a two-dimensional checkerboard layout, where qubits only interact with their direct geometric neighbors. While highly forgiving of initial errors, the surface code possesses an inefficient encoding rate. Because information is protected strictly by physical proximity, stabilizing a single logical qubit requires an overhead of 1 to 2,000 physical qubits. To resolve this severe inefficiency, quantum theorists introduced quantum low-density parity check, or QLDPC codes. These frameworks utilize sparse parity check matrices to encode multiple logical qubits into a single shared block of physical hardware. This table details the overhead efficiency of the traditional surface code against IBM's specific QLDPC implementation, the bivariate bicycle code. As shown, the bicycle code yields a physical-to-logical ratio of 24:1. By utilizing the shared block structure, the gross code variant successfully encodes 12 highly protected logical qubits within just 288 physical qubits. This achieves a 10-fold reduction in hardware over previous methods. To achieve this density, QLDPC codes relax the requirement for nearest neighbor interactions. By utilizing structured, non-local connectivity, the system can encode multiple logical qubits into a single shared block of physical hardware. This shift from local 2D protection to global graph protection enables the high encoding rates needed to support hundreds of logical qubits without a proportional explosion in physical hardware. With logical qubits stabilized, the system must force them to interact. Engineers primarily use lattice surgery, a spatial technique where adjacent logical patches are temporarily merged along their physical boundaries to entangle their states. However, mathematical theorems dictate that topological architectures cannot natively execute universal non-Clifford gates, such as the T-gate, without leaving their highly protected code space. To bypass this limitation, architectures employ magic state distillation. The hardware prepares numerous noisy physical states and forces them through an algorithmic filter, sacrificing the vast majority to extract a single, highly purified state. This purified magic state is then teleported into the main algorithm to execute a single advanced gate. Historically, the continuous distillation factories required to fuel this process consumed upward of 90% of a computer's total spatial and temporal resources. To target this massive inefficiency, researchers developed a highly optimized protocol called zero-level distillation, recently demonstrated on hardware by Quera. Instead of distilling at the complex logical level, the system executes rigorous fault-tolerant verification directly at the physical level. Purifying the states before they are injected into heavier encodings compresses the total spatial and temporal overhead by a factor of 8. Compressing the magic state distillation footprint significantly reduces the spatial and temporal overhead that has historically dominated fault-tolerant architectures. The combination of high-rate QLDPC codes and zero-level distillation reduces system resource estimates, compressing the timeline for executing utility-scale applications. In global cryptography, early estimates suggested breaking an RSA 2048 key would require 1 billion physical qubits. Due to dense encoding efficiencies, that requirement has plummeted to fewer than 100,000. In computational chemistry, humanity relies heavily on the Haber-Bosch process to produce agricultural ammonia fertilizers. This requires extreme temperatures and pressures, accounting for nearly 3% of global carbon emissions. Natural bacteria execute this exact conversion at ambient room temperature using the FE-MoCo enzyme. Creating an exact quantum simulation of this mechanism's highly entangled electrons now requires roughly 1,500 error-corrected logical qubits. These precise molecular energy models are actively moving into production, with companies like Quantinium executing end-to-end computational chemistry workflows on logical qubits today. While physical hardware platforms provide the raw computational capacity, it is the silent, complex orchestration of quantum error correction that enables the practical application of quantum advantage.